In this lesson, we will discuss electromagnetic radiation. Electromagnetic radiation occurs when any sort of electrical charge, such as an electron, undergoes acceleration. For example, in white light bulbs, heat causes the atoms in the wire filament of the bulb to vibrate back and forth. This oscillation produces electric and magnetic fields that travel away from the light bulb, which we view as light. Let's take a closer look at these electromagnetic fields. Let's first look at the field at a particular point in time. Imagine we have a line of charged particles equally spaced along our x-axis. When we turn on our light source, such as the light bulb we mentioned earlier, these particles will all feel a force pushing them from their initial position. These vectors show the magnitude and direction of the force the particles at that location feel. If we drew a line to connect all these vectors, we can see the variation in the field as we move out along our line of particles. The distance between two adjacent points of maximum magnitude of the wave is known as the wavelength and is represented by the symbol lambda. Let's now take a look at the field at a certain location. This time, let's imagine we have a single charged particle, and after turning on our light source, we monitor the magnitude and direction of force the particle feels. These vectors represent this force over a period of time. Once again, connecting the vectors, we can see the variation of the electric field over time. A good way to think of this is imagining yourself standing in a wave pool. As a wave passes you, you'll be pushed up, then back down again, and then back up again when another wave rolls by. This is what's happening to our charged particle as our light wave passes by it. The time between the 2 points of maximum force that the particle feels is known as the period and is symbolized by a capital T. The waves we focused on here are electric field waves, but the same holds true for magnetic waves. The magnetic field occurs along with the electric field, but lies in the plane perpendicular to the electric field. So, lambda represents the wavelength, which is measured in meters. Capital T represents the period, which is measured in seconds. The inverse of the period, or 1 over the period, is represented by the Greek letter nu and symbolizes the frequency of the wave. This tells us the number of times per second the field reaches its maximum value. Using the wavelength and frequency of light waves, we get the relationship wavelength times frequency is equal to c. c, the speed of light, is equal to 2.998 times 10 to the 8 meters per second. Relating this to all waves, not just light waves, the wavelength times frequency is equal to the speed of the wave.